everyone. The purpose of this video is to finish up our topic on acid-base titration with a last example of a weak acid reacting with a strong base. And so remember, we're going to see 4 different moments in time. Right, we've got our initial state before we add any of the strong base, the pre-equivalence point before we've reacted all of that strong base and that weak acid, the equivalence point where all of the weak acid has reacted with the strong base, and then the post-equivalence point when we've got excess strong base left over. So remember, the first step is to determine what is that equivalence point. And just to shorthand this a little bit, we've seen in a previous example how to calculate that. You take the volume and the concentration that you know, figure out the moles of that. That will give you the moles of the sodium hydroxide, and then you can take the moles and the molarity and find the volume of sodium hydroxide. But just like the previous example, we've got twice as much concentration of sodium hydroxide, and so we need half as much of the sodium hydroxide. And so the equivalence point is at 25 milliliters of sodium hydroxide. Okay, so go back to that previous video if you want to see how we calculate that. So starting out with the initial state, we've got 0 milliliters of sodium hydroxide. And so we're looking at pure weak acid. And so this goes back to those Ka expressions, those acid ionization expressions. You can do out the ice table if you want to, but just remember that in general, as long as we can assume the 5% rule, Ka will be equal to x squared over 0.100. Right, it's the x squared over the original concentration of that weak acid that they give us here. And the Ka value, if we don't know that, I think we know that from a previous example, or this is formic acid. I can add it in here. Ka for formic acid is equal to 1.8 times 10 to the negative 4th. Okay, so that would be given to you. We can plug that in for Ka and solve for x. X will be equal to the square root of 1.8 times 10 to the negative 4th multiplied by that concentration of 0.1 of the original concentration of the acid. And what does X stand for? Remember that X, if we're dealing with Ka values with weak acids, that is going to be the hydronium ion concentration at equilibrium. And so that's how we'll find our pH. And X equals 0.00424. And taking the pH, which equals the negative log of that concentration of the hydronium ions, and 2 significant figures, because that Ka is 2 significant figures, we get 2.37. Okay, so we can already see that that pH without any base is higher than the pH that we saw with the strong acid, right, which was a pH of 1. Okay, so now we're going to add that strong base next. We're looking at the pre-equivalence point, 15 milliliters of sodium hydroxide that's been added. And this one is where it starts to get a little fun, okay? We have seen, I believe, a strong base reacting with a weak acid, and so we are going to have to create a BCA table before we can use the Henderson-Hasselbalch equation. So our first step is going to be to take the sodium hydroxide concentration and the volume and figure out the moles. Right, again, because the volumes are changing as we're adding and reacting things, we need to find everything in moles, plus our BCA table tends to be in moles. So we're going to take the 15 milliliters of sodium hydroxide and convert that into liters, which gives us the 0.0150 liters. Multiply that by the concentration of the sodium hydroxide in order to get the moles. Liters cancel, and that will give us the 0.00300 moles of sodium hydroxide. And remember, if we are at the pre-equivalence point, then the titrant must be our limiting reactant. Okay, so that's going to be what is the change in our BCA table and what will be used up. So because it is a strong base, it's going to react with that weak acid, where we have the weak acid, HCOOH, and sodium hydroxide. Remember, that is the same thing as moles of the hydroxide ions. So it will be the hydroxide ions that react with that weak acid and leave us with the conjugate weak base, which would be our formate ion, HCOO negative. And of course you're going to have water on the end here, but we don't care because that doesn't help us with any of our expressions. So create that BCA table. And we start out without any of our conjugate base. We have so many moles of hydroxide that we've already calculated. That's that 0.003. And then we need the moles of formic acid, which I believe maybe we have not calculated that yet. But it should be 0.005. Okay, so we can calculate that real quick. Moles of formic acid will be the volume of formic acid, the 50 milliliters. So as 0.05 liters times the concentration of 0.1. And that will give us the 0.005. And we can plug that into our BCA table, so 0.005, and subtract out the limiting reactant until there's nothing left. So that's minus 0.003, which gives us nothing left over, and then minus 0.003 will leave us with the 0.02. And then of course that will give us the same amount as the change for the amount of conjugate base that we have left over. So that's 0.003. Okay, so we have moles of our acid and our conjugate base, and now we can look at the Henderson-Hasselbalch equation. But keeping in mind that our BCA tables are always in moles, right? So we first got to take the moles of each one of these and convert them into liters. And remember, we're looking for the total volume. And the total volume is the 15 milliliters of sodium hydroxide that we added to the 50 milliliters of the formic acid. And so total, we've got 50 plus 15, which gives us that 65 milliliters. So we've got to divide each one of the moles by 0.065 liters. Okay, and that will give us the concentration of each. So the concentration of formic acid again coming from over here, that is equal to 0.0307, and the concentration of our conjugate weak base coming from here is equal to 0.0461. All right, so I've got those two concentrations. I'm going to carry that over onto the next page and use the Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation, we've got the pH is equal to the pKa, that's the negative log of our Ka value of 1.8 times 10 to the negative fourth, and then add that to the log of the concentration of the weak base right over the weak acid. So it'll be the log of 0.04615 divided by the concentration of the weak acid. And so overall, we will get a pH of 3.74, two significant figures, 2 digits out, plus the 0.176. So a total pH of 3.92. And again, that is before the equivalence point. So now the next example, we will be at the equivalence point. Okay, when you are at the equivalence point, all of the acid and all of the base will be completely reacted. And so the only thing that matters at that point is the amount of conjugate base. So let's see. You should have let's write this out real quick so we can see what's going on. We've got that formic acid reacting with the sodium hydroxide, forming the conjugate base. Plus water. And of course we have that sodium ion that's inertly floating around. So we don't care too much about either one of those. And we know that we have 0.005 moles of the formic acid. And that's going to react with, of course, 0.005 moles of that strong base. So all of that is going to react, and you could draw out a BCA table if you'd like, but it will react to form the 0.005 moles of your conjugate base. Okay, and so that's what's in solution is your weak conjugate base. And we can find the pH for a weak conjugate base by finding the concentration, using that Kb expression, and then solving for the hydroxide ions. So we'll take the moles of that conjugate base and divide by the total volume of the solution. Of course, you have the 50 milliliters starting out plus the 25 for a total of 75 milliliters. Okay, so we'll take that moles of the weak base and divide by the milliliters in terms of liters, 0.075. and that will give us a concentration of 0.06 repeating. Okay, and that is of course the concentration of the weak base. So we're going to need to use the Kb expression for a weak base. Remember, we were given Ka, so Kb will be that Kw value 1 times 10 to the negative 14th divided by the Ka that we know, which is the 1.8 times 10 to the negative 4th. And we get Kb equals 5.56 times 10 to the negative 11th. Okay, and we know that Kb is going to be equal to x squared over the original concentration of that weak base. So 0.066. And again, you could do an ICE table if you needed to. And then we will solve for x. And remember what x stands for. If we're looking at a Kb expression, it's not the hydronium ion, it's the hydroxide ion. Okay, so that hydroxide ion is equal to x, and x would be the square root of the 5.56 times 10 to the negative 11th times the 0.06 repeating. And so we get x equals 1.93. That 3 is subscripted, it's insignificant, times 10 to the negative 6th. Okay, and once we have that hydroxide ion concentration, we can calculate the pOH, right? So the pOH will be equal to the negative log of that hydroxide ion concentration. Out 2 decimal places will give us 5.71. And then, of course, to find the pH, we'll have to do 14 minus that value. So 14 minus the 5.71 will lead to 8.29. Okay, so just to summarize, when you are at the equivalence point with a weak acid and a strong base, basically all of the weak acid that you have, that 0.005 moles, will react to give you 0.005 moles of the conjugate base. And from that point, you're looking at the Kb expression and a pure conjugate base and trying to determine the pH of that, which is review from old material. But that's where you have the Kb equals x squared over the original concentration of that weak base. Keeping in mind that x in that expression represents the hydroxide ion. Okay, and we got one last example. Oh, we'll have to erase this. The last example is if we go past the equivalence point and we do 30 milliliters. So at this point, we've used up all of the sodium hydroxide, which was 25 milliliters. And so we have 5 milliliters of excess sodium hydroxide. And so at that point, we don't really care about the conjugate acid-base pair because that sodium hydroxide is going to take over everything in terms of the pH. And so we'll use that 5 milliliters of sodium hydroxide, determine what the concentration of the hydroxide ion is, and use the pH, or figure out the pH from that. So 5 milliliters of sodium hydroxide, let's figure out how many moles that is. Because again, we're changing volumes, so we got to find the moles and then divide by the new volume. So 5 milliliters, converted into liters would be 0.005 liters times the concentration of the sodium hydroxide, which is 0.2. Liters cancel, and that will give us the moles. So I'll just rewrite that. 0.001 moles of sodium hydroxide. And of course, that tells us the amount of moles that we have of the hydroxide ion. Okay, but to plug that in for POH, we've got to have it in concentration. And so we'll take that mole of sodium hydroxide and divide by the new volume. So the total volume of the system is the 30 milliliters of the sodium hydroxide plus the 50 milliliters of the original formic acid, for a total of 80 milliliters. Okay, so we'll take that mole of sodium hydroxide and divide by 0.08 liters, and that should be 800. And remember, that is the hydroxide ion, so the concentration of the hydroxide ion will be equal to 0.001 divided by 0.08, giving us 0.0125 molarity of the hydroxide ion. And the last step is to plug that in for the equation of POH. And so POH will be equal to the negative log of that concentration. We get that that is 1.90. And last step will be to change it to pH. 14 minus the 1.90 gives us 12.10. All right, and if we go back and look at, so the strong acid, we did 40 milliliters, so it will be slightly different, but there it was 12.5, and with 30 milliliters, it was 12.10, so pretty close there. But that should end our topic in the overall section of acid-base equilibria.